Approximations. Composite bodies and figures approximation. When a body or figure can be conveniently divided into several parts whose mass center are easily determined, we use the principle of moment and treat each part as a finite element of whole. When a body or figure can be conveniently divided into several parts whose mass center are easily determined, we use the principle of moments and treat each part as a finite element of the whole. Such a body is illustrated symmetrically in this picture. Consider this picture. In this picture, its parts have masses m1, m2, and m3. Its parts have masses m3 with their respective mass center coordinate. x1, x2, and x3. So we can write this relation. For a moment in the x direction, the moment say that m1 multiplied 2x1 m2 x2 m3 x3 should be equals to the total m, which is m1 m2 plus m3 multiplied to the x bar. So x bar for the total shape sigma m x bar sigma m. We can write for body in 3 dimension and for the composite bodies. And figures. X bar bar. Analogous relations holds for composite line areas and volumes, where the m's are replaced by L and A's and B's respectively. Now we can, for figures, we can write this expression sigma m sigma A L x bar sigma L y bar sigma L y bar sigma L and z L z bar on sigma L. For the y in the two dimension, A x bar sigma A and z the volume case, we have this relation x bar vi x bar sigma vi and z bar Note, if a hole or cavity is considered one of the component parts of composite body or figure, the corresponding mass represented by the cavity or hole is treated as negative quantity. An approximation method in this case in practice, the boundaries of an area or volume may not be expressible in terms of simple geometrical shapes or as shapes which can be represented mathematically. For such cases, we must report the method of approximations. As an example, consider the problem of locating the centroid C of the irregular shape of this example. In this example, the area is divided into a strip of delta x and variable height h. The area A of each strip, such as the shown in the picture, h delta x, and is multiplied by the coordinate for the centroid element xc, yc, and zc. Obtain the moment of element area. The sum of moments for all strips divided by total area of the strip will give the corresponding centroidal coordinate. A systematic tabulation of the result will permit the orderly evaluation of the total areas. The summation of the moments and moments of areas and central coordinates can be written as this relation: x bar axc on sigma a and y bar AYC on my A. We can increase the accuracy of the approximation by decreasing the width of the street. In all cases, the average height of the strip should be estimated in approximating the areas. Although it is usually advantageous to use elements of constant width, it is not necessary. In fact, we may use elements of any size and shape which approximate the given area to satisfactory accuracy. For the irregular volume, we have also some irregular volume. To locate the center of an irregular volume, we may reduce the problem to one locating the centroid of area. Consider the volume shown in this picture, where the magnitude A of the cross-sectional area normal to the x direction are plotted against x as shown. The magnitude x here the vertical strip of area under the curve is A delta x, and xc is centroid. Thus, the centroid of the volume can be calculated as sigma x vxc on sigma b. V is the volume of each part. The next section is about the theorem of Composite.